Anyway, right, on this one. So you might, on this one, I could see where it wouldn't be a bad idea to maybe draw a picture at first. Then you can turn that into a free body diagram afterwards. Definitely in the future, we're going to want to draw pictures. Like when we move this on to situations where we've got a crate sliding down a ramp or something, then you want to have a picture probably. Yes?
Is frictional force downward or is it just moving up?
Okay, what do you think? Here's the question.
It's just the opposite of the direction.
Yeah, it is, isn't it? Like if I slide this along the desk, by pushing force is in that direction, isn't it? I'm being resisted. I'm being resisted in that direction by friction. Right? Okay. We'll talk a lot more about friction in the future. So there's the tension force, right? Everybody agree? Okay, tell me what else to put on this thing. What else is going on?
Friction is going in the opposite direction.
Okay, so we've got friction pulling in that direction. I'm going to assume it tells us that it is accelerating, right?
Yeah.
So I'm going to make the friction vector a little bit smaller than the tension vector, right? Okay, is that it? Are those the only forces acting?
No, friction is the third.
Okay, there are some other forces, aren't there? So one force for sure, we know that gravity's acting on this thing, right? Okay, is that it? Does that look right? If I add those vectors up, what's the resultant going to look like?
It's going to look weird.
It's going to look weird. It's going to have a right component and a down component. But in your experience, when you do something like this, when you pull the crate across the ground, we've all done stuff like that, does the crate burrow into the ground?
No.
No, we must be missing a force. Something
Unless
else.
it's on soft dirt.
Say it again.
That's the force acting that's pushing the thing up.
Ah, okay, yeah, there must be some kind of a surface force acting, right? The ground is pushing up on the object. The proof of that would be, what if I were to set this down on a surface that was like covered in Play-Doh? This would make an imprint in the Play-Doh, right? And then it would probably stop because at some point the Play-Doh could push up hard enough that it would stop sinking, right? It would get thin enough maybe, right? So we can all agree that like if I hold this in my hand, there's the weight pushing down of gravity, and then there's my hand pushing up to offset that. Well, the table's taking the place of my hand, or in this case, the floor is, right? So we've got this other force, which we will talk much more about later, but what this force is actually called is a normal force. It's a normal force. The word normal in math just means perpendicular. So it's the force that's acting perpendicular to the floor. You can think of it as the supporting force.
So if you're ever pulling something on the ground, the normal force and gravity just offset? Basically.
Yes, exactly. And when I'm standing here, my weight and the normal force from the floor offset. Okay? Yes?
So if you were to have a normal force that's greater than the gravity pushing it down, would it become lighter?
It wouldn't become lighter, but it would elevate above the floor, which never happens. So the normal force must always adjust itself to be equal to gravity.
Like what if you kind of blew up?
Well, then we'd have an additional force, another tension vector up there, wouldn't we?
So instead of going that way, would it go more like that way? Or
Yeah.
would it still go right?
It would. Yep. Okay? Yeah, and we'll deal with some problems like that in the future, where it doesn't just go straight. Okay, but now, when so we added all these forces, but we might just turn around and subtract a couple of them. Because for the purposes of our discussion here, what's gonna be the path of this object? We already know what it's gonna do. It's gonna move to the right, isn't it? So is there going to be, what's gonna happen to the purple and green forces? They're gonna cancel, aren't they? Right? Later on, we'll deal with situations where they don't cancel. But for now, fortunately, they do. And so we could just get rid of those because when we're drawing the net force, they don't really contribute, do they? Right? But the other two do contribute, right? If we draw our free body diagram that comes from this, let's just say, I'm just gonna go right to the net force. Okay, instead of redrawing the same picture with a dot instead of a crate. The net force, would you agree, is gonna look like that? Okay, so how am I gonna find the net force here? Yeah, I'm gonna plug everything in. I know some stuff, don't I? I know that the tension force is what I'm looking for, right? The frictional force is 30 newtons, and I know the acceleration. Okay.
And the weight of tension minus
Okay.
equals the mass times the-
Yeah, so the net force here, would you agree that the net force is gonna be, the net force is gonna be this one plus this one. This has a positive magnitude, right? The magnitude's always positive, but this is a positive force, this is a negative force, because it's pushing in the negative x direction, right? So we could think about this then as being the magnitude of tension minus the magnitude of friction is our net force, right? Everybody agree? Okay, and that's got to equal MA. Agreed? Okay, well, we know A, we know M, we know the frictional force, so we've really got an equation here where I could just plug and chug and solve for F sub t, couldn't I? Right? If I plug in all the numbers, what do I get? I get F sub t minus 30 standard units equals 50 times 0.25, right? So what is that, 12.5? Okay. So what do I have to do to find the tension?
So you're add 30.
Yeah, I'm just gonna add 30 to both sides, right? And I get F sub t equals 42.5, and the units would be newtons. See how we did that? Okay. We will come up with a much better way of organizing that later. Okay, we'll set up what's called equations of motion and solve the equations of motion to find the acceleration or the missing force. But for now, does everybody follow our logic on this?
So is tension always gonna be positive?
Tension, well, no. What defines positive or negative?
The direction.
The direction, right? So our convention. So if we're dealing with like normal XY coordinate plane, arbitrarily that's positive and that's positive, right? Did it matter? Really, we were just asking for a magnitude here, right? We wanted to know what's the magnitude of how much tension is in the rope. So I could have just as easily drawn the tension going that way, because we never really were told in what direction we were pulling this thing, right? Wouldn't have made any difference. If I had drawn the tension going that way and the frictional force going that way, well, my answer would have been the same, right? True, the net force would have been negative instead of positive, but we were just asking for the amount of tension, the magnitude, right? So it really didn't make any difference.
So like, is there ever gonna be an instance where tension is like a truly negative?
Yeah, there will be. I'm going to do an example today where you'll see that, a physical example today where you'll see that. Okay, and now all that would mean is tension is like pulling down, for example. Okay. All right, so those three examples kind of illustrate how how you can use Newton's second law to solve a simple equation based on Newton's second law. Okay, so moving on. Next question. I want to know, what is the motion of an object with no forces acting on it?
Isn't that undefined?
It's not. It's not. We can describe the motion of an object with no forces acting on it.
It could be in any direction or still, as long as it's not.
Would it just be like
Ah,
free
okay.
floating?
It could be free floating. It could be stationary. Where's probably the best place to contemplate a situation like this? Imagine, deep space, right? Probably the best way to think about it. So if an object is at rest in deep space, what do you expect it to always do? Well, it's just going to stay there, right? If it's in deep space, so there's no forces acting on it, truly no forces acting on it, then what's its motivation to ever move, right? It just stays there, okay? What if it's gliding through deep space with a velocity of 10 meters per second relative to something we all recognize? It's going to stay at that, isn't it? Right? Everybody agree? Okay. So that's a pretty easy concept. That's Newton's first law. Newton's first law, the law of inertia, the way it's described in the book, just says an object that is at rest will remain at rest, and an object that is moving will continue to move in a straight line with constant speed, if and only if the net force acting on it is zero, right? Think about the opposite of that. Think about the converse. If the net force acting on it were not zero, then it would be accelerating, right? So this can only be the case if the net force acting on it is zero, right? So another way of saying that would just be an object at rest will remain at rest, object moving will remain in straight line motion, unless acted on by an external force. Now that's kind of an important word. Sometimes we talk about, this definition I like in a way because it references an external force. What's an external force mean?
Pressure pull.
Okay, a force. Now, how is this different? Like if I'm in the car and my daughter is driving, I have a tendency when we move to a stop sign to push against the floor with my feet. Right? I'm applying a force to the front of the car, but it's not doing much good.
No.
How come?
Because she's not doing part of the movie.
Don't jump right into this either, please. Because that's an internal force, right? That force is inside the car, isn't it? So it's not really going to do any good.
But if you jump,
Whereas if she hits
if you were
somebody,
that would be right.
I mean, external force.
Right. An external force would be if the tires, if you put on the actual brakes, and then the tires create some friction with the ground, and then the ground's pushing back on the car, and so that's a different story, right?
What if you somehow put your foot on the tire?
Well, okay, that becomes maybe causes an external force.
the force would be acting on the car more as on its foot.
Anyway, point being that the force has to be acting on the system that we're talking about, like the car or the spaceship or something, right? So once you have that though, then you can change the motion and it's no longer inertial motion. So the law of inertia, I mean, what is this? We talk about this thing, inertia. And this was originally talked about by Newton. He talked about the inertia of an object. The inertia is just defined as the tendency of an object to maintain its motion, right? So I'm going to give you two examples of objects. You tell me which one has more inertia, a truck or a Toyota Prius. The big truck probably has more inertia, right? Because its tendency to keep its current motion is much greater than the Prius's is, right? The Prius, you don't have to apply a lot of force to it to coerce it to change its motion, but the truck you do. So inertia is kind of a qualitative thing, right? We all know what it means. We all have a pretty good idea what it means. If we want to attach some units to that and some numbers and make it quantitative, what are we probably talking about in reality when we say inertia?
The mass.
The mass, yeah, right? Inertia really evolved into the quantitative concept of mass, which we all recognize. It's measurable. Inertia really isn't. Inertia is just an idea, right? Okay, so given that then, I want to know, how are these situations the same and different? A 1,000-kilogram spacecraft moves through deep space with its rockets off. Okay? A 1,000-kilogram car drives a flat, straight section of road with its cruise control on.
There's gravity acting on the car.
Okay, so it's different because there are forces acting on the car, right? Everybody agree? There are no forces acting on the gliding spaceship. Okay, but how are they the same?
They're the same mass and they're going in a straight line.
Oh, okay, they have the same masses, yeah, but they have no acceleration. So what is the net force acting on both of those? Zero, yeah. They both are experiencing a zero net force. It's just that the spaceship actually has no forces acting on it. The car has a bunch of forces acting on it, but they all balance, right? They all cancel each other out. So we'd say these are two cases of equilibrium. Right? Because all the forces are balanced. There's a zero net force, right? That makes sense? Now, you probably couldn't tell the difference. I mean, well, how often are you in a spaceship gliding through space? But you probably couldn't tell the difference if you woke up from a nap and that was a normal part of your daily routine was to glide, through space in a spaceship. You might not know if you're in the car
Well,
driving down the
there
road.
wouldn't be any gravity in the spaceship, so.
Okay, well, I guess maybe you would know.
Is
Yeah.
it more realistic
Yeah.
for the car or the spacecraft to weigh 1,000 kilograms?
The car, I think. Yeah.
So it'd be like,
Spacecraft,
it'd be
that's
Okay, so
mini.
you got it. Okay, last one. Mass versus weight. Mass versus weight. I've got
You have 6 minutes to destroy.
Oh, okay, I can do
American
this. I can do
system.
this. This is good. So mass versus weight. Mass is an invariant property of an object, and weight is not, right? Okay, so I want to know then if you are going to kick a ball of, you don't know anything about it. You just know that it's a ball that's sitting there. Let's say it's black and you don't know much about it. What's more important to you, the mass or the weight? So I want to know, or does it matter?
I'd say I don't know if it matters.
Okay, not know if it matters, right?
cause if
Okay.
it's 100 pounds.
Because okay, if it's 100 pounds, then it's got a certain mass, but either way,
Yeah,
it's
it's
gonna
weight.
hurt, right?
Either way, yeah.
Okay, I'm gonna prove you wrong.
Yeah, it's weight, because
Okay.
if you're on a really small planet with low gravity, then it's gonna be like
Alright,
10 pounds.
Ah,
The mass doesn't change, but the
Okay.
weight does.
so let's go into outer space.
So the weight
Let's take
does.
the whole experiment into outer
So
space.
okay,
What's-
then
what's-
the mass?
What's the weight of the ball in outer space?
Instead of the weight.
No,
It'd be zero.
the weight is zero because the weight is the gravitational force, right? And so in outer space, the acceleration of gravity would be zero, and so it would have no weight. But the mass, did it change? No. And so if you fire up your retro rockets and you come flying into this thing and you're gonna kick it in your spacesuit, let's say it turns out that it's a bowling ball. So it's still gonna break your foot, even if its weight is zero, because it's got a lot of mass, right? The mass is truly a property of the object. What the mass really represents is all of the stuff, all of the matter that's encompassed in that object. Now, matter looks different depending on the form it takes. Styrofoam looks different than lead, right? But imagine that you took a 1 kilogram, a big 1 kilogram piece of styrofoam, and a little 1 kilogram piece of lead, and let's say you broke those apart into their constituent subatomic particles. And somehow we could gather up those subatomic particles and make two piles. What would you notice about the two piles? Be the same, right? They're just put together in different ways to form different elements and different types of matter, right? But the two piles would be the same because they have the same mass. So the mass really is measuring the amount of universal stuff in it, but the stuff can just be packaged differently, right? Yeah.
Would we have to get 1 mole of each, or would we be fine getting 1?
No, I'm just gonna say one kilogram. That's all we need. All we need is a mass here. Yep.
And they would both be the same amount of.
If you could do that, which is a stretch, I mean, if you could strip them down to, let's say, we're gonna strip them down to quarks. If we made two piles of quarks, the two piles of quarks would be identical.
So we don't have to worry about moles or anything?
No, we
as
don't
long
have
as
to.
they're the
Nope.
same weight?
Nope, mass is all it takes. So here's the last thing I wanna do then. This has got some relevance to you when you go grocery shopping. I'll explain why in a second. So I've got this little piece of wimpy string and I've got this hanging mass here. I have the ability to break the string either on the top or the bottom, either one. How about if I do the bottom first? I can do it, I promise you. I don't believe you. Well, I'll prove it to you. I broke the bottom. Want me to break the top? No, I didn't. I'll prove it. There's the same kind of string right here. I will now break the top instead. Want me to break the top? Well, I better put my crash pad down here. I almost forgot. Scrap the old physics lab books, yeah, they don't work.
Take that previous years.
That's right. Okay, I'll break the top.
That was cool.
How did I do that?
Good job.
Sudden pressure or?
Okay, so in the first case where I broke the bottom one, what allowed me to do that? The weight or the mass of the hanging object?
Mass.
The mass, the inertia, right?
Because
Because it's resisting that sudden acceleration,
Yeah.
agreed? So if I snap the string down, the mass of the object, it's hard, because it's got inertia,
That one was.
it takes a lot of force to get it accelerating, right? And so its own mass protected the string on the top from the sudden impact, right? Agreed? The second time, what was more important, the weight or the mass?
The weight.
The weight was, because it was the same string above and below, but the string above had to support the weight of the object plus the additional tension in the bottom string, right? If I pull slowly, so the object in the middle can react to the pull, I gradually increase the tension in the bottom string. Well, the bottom string only has to withstand the tension I'm providing. The string on the top has to withstand that tension plus the additional weight of the object, right? So when you go to the store and you got your handful of carrots and you wanna pull off one of those, well, what you might do? You wanna pull off one of those, those little bags to put the carrots in, the produce section? But you only have one hand, so you can't hold it and tear it. What do?
You gotta go quick.
You go quick, so you utilize the inertia of the roll of bags, right?
That's what my
See?
mama told me to do, she's like, you need to consider the inertia of you really think you're gonna go slow? How is the mass? Come on, think.
No, every time I pull up, it's valuable. Look at